On 7th August 2024 in Ahmedabad, a 20 years old young man was sleeping at his home while charging the battery of his e-scooter at the drawing room. The battery exploded at 4:30 hours in the early morning, and luckily the young man and his family escaped out of this incident. Very recently, Hyderabad Consumer Court directed a reputed electric vehicle company to pay hefty amount to the EV owner whose car caught fire while running. Thus, there are multiple instances of lithium battery explosions of the electric vehicles. But solely blaming the companies for their products would be worthless, because at least they are making their efforts to develop the necessities of the humankind. But why these lithium-ion batteries are so prone to catch fire? One explanation was given in my last video. I will discuss all the reasons in this video and their probable solutions. In my last video of extreme fast charging lithium-ion batteries, I discussed what a lithium-ion battery is and its working mechanism. I request you to watch the video first before toggling to this one. A lithium-ion battery undergoes thermal runaway when it gets deformed, like through the accident of the electric vehicles, where its anode and cathode gets disintegrated, resulting short circuit. Thermal runaways of the lithium-ion batteries may also occur for the defects inside the battery due to the aging of the battery or due to the lithium plating and dendritic formation upon overcharging. Roughened up build quality of the lithium-ion batteries and auto cutoff upon overcharging may reduce the risk involved in the thermal runaways of the batteries. The heat generated in the lithium-ion batteries can be divided into two parts. One, irreversible heat, and the other one is reversible heat. Irreversible heat is generated in the lithium-ion batteries due to the Joule's effect according to the equation. That is, upon fast charging with high current or upon high internal resistance of the lithium-ion batteries. Whereas reversible heat is generated inside the lithium-ion batteries due to the diffusion of the lithium ions, due to the chemical reactions in the cathode and anode of the lithium-ion batteries, or due to any other exothermic chemical reactions occurring inside the battery. Reversible heat generation is of 6 to 7 times higher than the irreversible heat generation inside the lithium cobalt oxide batteries. Thus, modification of the components of the lithium-ion batteries to reduce the reversible heat generation or to withstand certain threshold temperature might be the best possible way to reduce the battery's thermal runaway. The lithium-ion battery mainly have 4 main components: the cathode, the anode, the electrolyte, and the separator. Hence, modification of each of these 4 parts of the lithium-ion batteries may reduce its thermal runaway. First, modification of the anode materials. Solid electrolyte interface, or ACI, is a layer that is formed on the surface of the electrodes as discussed in the previous video. The ACI has much significance in controlling the battery's thermal runaway because the ACI controls the chemical reactions on the electrode surface and hence prevent the electrodes from overheating. Thus, the stability of the ACI is much important. In order to do so, artificial ACIs are made on the graphite anode, such as through the atomic layer deposition of the alumina on the graphite anode. This shows better thermal stability of the graphite anode. In recent cases, thermal responsive polymers are also coated on the graphite anode. This is because when the internal temperature of the battery exceeds certain level, the polymers melt and forms the non-conductive barrier of the lithium-ion's transportation to the graphite anode, resulting shutdown of the lithium-ion batteries. In most recent cases, the graphite anodes are also being replaced by some other anode materials like lithium titanate, and this shows much better thermal stability than the ordinary graphite anode lithium-ion batteries. Second, modification of the cathode materials. In replacement of the lithium cobalt oxide cathodes, various other lithium metal oxides or lithium metal salts have been deployed to check the thermal stabilities of the lithium-ion batteries, such as lithium manganese oxide, lithium nickel manganese oxide, lithium nickel cobalt aluminum oxide, or lithium iron phosphate. Among all these cathode materials, lithium iron phosphate shows exceptional thermal stability, and it is also cheaper than the other cathode materials. The other problem with these lithium metal oxide cathodes is that this lithium metal oxide release oxygen during heating. This oxygen reacts with the electrolytes, creating defects inside the battery that may risk the battery's thermal stability. The release of oxygen by these lithium metal oxides can be reduced by changing the stoichiometric ratios of the metals or the use of the metal combinations in the lithium metal oxides as cathodes. Here also thermal responsive polymers are coated on the cathode to shut down the battery when certain threshold temperature is reached. Third, improving the electrolytes of the lithium-ion batteries. Currently, lithium salts like lithium hexafluorophosphate dissolve in organic solvents like diethyl carbonate, dimethyl carbonate, etc. are used as electrolytes in the lithium-ion batteries. But unfortunately, these organic solvents are highly insoluble and highly volatile that may pose the threats of the battery's thermal runway. Room temperature ionic liquids and solid state electrolytes like lithium lanthanum zirconium oxide can be good alternatives to these organic solvents as they are non-flammable and non-volatile. Fourth, modification of the separators. The job of the separator in the lithium-ion battery is to prevent the direct contact between the cathode and anode. As if this happens, then a short circuit will blow up the battery. The separator is also an insulator and having micropores in it through which lithium ions migrate back and forth. Currently, polyethylene and polypropylene are used as separators in the lithium-ion batteries. But the problem with these polymers is that upon heating, they shrank and may be unable to prevent the direct contact between the cathode and anode. So, thermally stable polymers like polyimide can do this job better in replacement of the polypropylene and polyethylene. Here also a thermal responsive polymer can be coated on the separator, which melts upon reaching certain threshold temperature of the battery, blocking the pores of the separators, inhibiting the migration of the lithium ions, and thus resulting the battery's shutdown. Thus, the use of lithium-ion batteries in the electric vehicles pose certain risks and threats, but the developments are there to avoid the same. And I presume that the electric vehicle market is still at its nascent stage to predict its future. The lithium-ion batteries were developed in order to address the crisis of the fossil fuel. But the metals used in the lithium-ion batteries, like lithium itself or nickel, cobalt, iron, etc., are also obtained by mining. So the resources and the availability of these metals in future are also the main concern of this industry. Issues like waste management or recycling of the lithium-ion batteries will be discussed in the next video. If you have any queries related to this topic, then please ask in the comment box. I will be happy to answer you. If you like this video, then share as much as possible and subscribe to this channel. We will meet in the next one.